When Kc or equilibrium constant is given, this is the equation that you're going to use. As well as E naught cell is equal to minus delta G naught by Nf. In an electrolytic cell, electrical energy is being converted into chemical energy. How much mass is deposited is going to be directly proportional to the quantity of electricity produced. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with session 3 of the chapter Electrochemistry. So in the last session we have discussed what is electrode potential as well as what is standard hydrogen electrode potential, that is She. How can it be used as an anode as well as cathode, right? As well as electrochemical series and a very important equation, Nernst equation, right? So in today's session we are going to see the thermodynamics of Nernst equation as well as we are going to start with the next set, that is electrolytic cell. So we are going to complete electrochemical cell today and we are moving on to the next one, that is electrolytic cell. So let's start with the thermodynamics of Nernst equation. In here what we are going to do is the Nernst equation, we are going to write it in terms of equilibrium constant for a cell reaction, work done by the cell and Gibbs free energy of the cell. So how the Nernst equation can be related within the equilibrium constant, work done and Gibbs free energy, we are going to see. So the first one, equilibrium constant from Nernst equation. Okay, so the equation is E naught cell is equal to 2.303 RT by log Kc. Okay, so we have already studied one equation, E cell is equal to E naught cell minus 2.303 RT by NF log of anode by cathode. Yes, this is one reaction. So this is one equation that we have studied on Nernst equation, right? Now Nernst equation we are going to write in terms of Kc, that is equilibrium constant. Now what is equilibrium constant? We already know that if we are taking a reaction AA plus BB giving CC plus DD, if it's a reversible reaction, how do we write equilibrium constant? It is the product of molar concentration of the products raised to the powers, which is equal to their number of moles, divided by the product of molar concentration of the reactants raised to the powers, which is equal to their number of moles. So this is Kc, right? So what Kc you are having here is this particular one, which is equilibrium constant. How to write that? We have already studied in last year itself, right? So this is the equation which relates E naught cell and Kc. Okay, so we already know what is R, T, N, F, all of that is already familiar to you. So if a question asks you to calculate the electrode potential of a cell or standard electrode potential of a cell, when Kc or equilibrium constant is given, this is the equation that you're going to use, right? The next one is relation between standard free energy change and E naught cell. So how the electrode potential and Gibbs free energy is related, we are going to see. This is a relationship between electrode potential and equilibrium constant. This is electrode potential and standard Gibbs free energy, right? So electrical work done is the product of the potential difference and the charge cell that flows, right? Which is the charge that flows in the cell. So it is the product of that. So work done is equal to E cell into charge. Okay, now the maximum work done on the surroundings is equal to the decrease in free energy. So work done is also equal to minus delta G naught. So this delta G is Gibbs free energy and delta G naught will be equal to E cell into charge. From where we are getting this equation? When work done is equal to minus delta G, I can use this minus delta G here. So that is what I am doing here. The equation becomes minus delta G naught is equal to E cell into charge. Now in last year when we have studied equilibrium and thermodynamics chapter, we have studied this particular equation that relates Gibbs free energy and electrode potential, which is delta G naught is equal to minus NF E naught cell, where N is number of moles, E is the electrode potential and F is Faraday's constant. We have already studied this particular equation in last year. Now, we already know this particular equation, that is E naught cell is equal to 2.303 RT by log Kc, RT by NF log Kc. We have just studied this equation in the previous slide. Now, what we are going to do is, From this particular equation, we can find another equation for E naught cell. Just rearranging this, E naught cell will be equal to minus delta G naught by NF. It comes from this particular equation. We know that delta G naught is equal to minus NF E naught cell. So we can write E naught cell as this delta G will remain as it is, minus delta G naught divided by this N and F will come to the denominator. Right, this N and F will come to the denominator. So that we are using here. I hope it is clear. Now we have two equations for E naught cell. E naught cell is equal to 2.303 RT by NF log Kc, as well as E naught cell is equal to minus delta G naught by NF. So what can I do? I can equate these two equations, right? Both of them are equal to E naught cell. So what happens? Minus delta G naught by NF is equal to 2.303 RT by NF log Kc. Now NF and NF can be cancelled out. So your final equation will be delta G naught is equal to, this minus is taken to the other side, minus 2.303 RT log Kc. So this is the equation, which is very important equation, which relates delta G naught, Gibbs free energy, and equilibrium constant. So I hope it is clear, right? So these two equations are very important to remember. Now the reaction parameters at the standard state, what does that mean is, when delta G naught is less than 0, right, your equilibrium constant will be always greater than 1. From here itself you can see, if this is going to be a positive value, this is going to be a negative value. You have a minus sign here. So what does that mean? Delta G naught, if it is less than 0, log Kc or your Kc will be always greater than 1. And if Kc is greater than 1, E naught cell will be of course greater than 1. From that equation you can see, if Kc is greater than 1, this is also going to be greater than 1, and the reaction is going to be spontaneous, right? Reaction is spontaneous means the reaction will take place on its own. Now if delta G naught is equal to 0, right? If delta G naught is equal to 0, then Kc value will be 1, E naught cell will be 0 at equilibrium. We already know that at equilibrium Kc value will be equal to 1, right? So it is at equilibrium condition. Now the next one is, if delta G naught is greater than 0, then your Kc value will be less than 1. Right, and what will happen to E naught cell? That will be more than 0. Now the reaction will be non-spontaneous. That means it will not happen on its own. The reaction will not take place. So I hope it is clear. Right, so this part you might be already familiar with. When delta G naught is less than 0, the reaction is spontaneous. We have studied in last year. So how it can be related to K, that is equilibrium constant, as well as E naught cell. I hope it is clear. Now moving on to the next part, that is electrolytic cell. So we have completed the discussion regarding electrochemical cell. Now we are moving on to electrolytic cell. So already we have an idea what is electrolytic cell. In an electrolytic cell, electrical energy is being converted into chemical energy. That means a non-spontaneous reaction is going to happen here. That means electricity will be provided, and due to the presence of this electrical energy, chemical reactions is going to take place. So a non-spontaneous reaction is made spontaneous by passing electricity through it, right? So it converts electrical energy into chemical energy. Now in this case, the electrolytic cell anode will be positive. In electrochemical cell, anode is negative, cathode is positive. Here anode is going to be positive and cathode is going to be negative. I hope it is clear. Now, unlike electrochemical cell, wherein you have two half cells which is connected by a wire and salt bridge, all of that. Unlike electrochemical cell, wherein you have two half cells, here in electrolytic cell you have a single cell only, right? Only one container you can see here, in which, that is, only one electrolyte solution will be there, in which both the electrodes are being dipped. Okay, so you can take an example here. Both of these electrodes are made of copper and it is dipped in copper sulfate solution. Okay, so here the process which is happening is actually purification of copper, right? See, this electrolytic method is actually used for purifying metals or coating metals over other metals. So here what is happening is, the same way connections are made, two electrodes are there and a connection is made, anode is positive, cathode is negative. One electrode acts as cathode, one electrode acts as anode, and one single electrolyte solution will be there, and These two electrodes are going to act as anode and cathode, right? So you can see positive anode will be there and negative cathode will be there. Okay. Now, what is actually electrolysis then? The decomposition of electrolyte solution by the passage of electric current, which results in the deposition of metals or liberation of gases at the electrode. So what is happening in electrolysis? That is, in electrolytic cell, electrolysis process is taking place. So what is electrolysis? Decomposition of electrolyte solution by passage of electric current. We are passing electric current through this electrolyte solution and reactions are going to take place. Either some substance will be deposited or else some gases will be evolved. So as I told before, this electrolytic process or this electrolytic cell is being used to purify copper. That is, purify any metals. It can be used. So in here you can see there is impure copper and pure copper, which is taken as the two different electrodes, and one single electrolytic solution is there. Let us assume that we have taken copper sulfate. Okay, because the electrodes we have taken here is copper. Now you have impure copper as which one? Anode, and pure copper as cathode. So whatever you have to purify, that is the impure one, impure metal is going to be always taken as the anode. The impure one will be taken as the anode and the pure metal will be taken as the cathode. I hope it is clear. Now what is going to happen here? In anode we know that oxidation will take place. Okay, oxidation is going to take place and Cu is going to get oxidized to Cu2 plus in this part, right? Cu2 plus is going to get formed. That is, Cu is going to get oxidized to Cu2 plus. And what will happen? The electrons are going to move to the other part, and in here the electrons are being accepted by the Cu2 plus. That is, in cathode, reduction takes place by the acceptance of Cu2 plus and forms Cu. So now what do you think will happen? The impurities are going to get deposited below the anode, right? This is undergoing oxidation. The impure one is undergoing oxidation, and what happens? The extra impurities is going to get deposited here. Electrons are going to move on to the other side, and here reduction will take place and copper is going to get deposited here on that particular electrode. So as the process continues, what will happen to the size of this? Impurities are going to settle down. The size of anode becomes smaller and smaller, and the size of cathode becomes larger and larger because the pure copper will be deposited here. So what you have to remember, in the process of purification of any metal, the impure one is going to be taken as the anode. It will undergo oxidation, right? Electrons will be formed, and the pure one will be taken as cathode, in which the Cu2 plus ions which is present in the electrolyte will accept the electrons, and what will happen? Cu will get deposited, copper will get deposited, and the impurities will be always present below the anode. So the size of anode becomes smaller and the size of cathode becomes larger. So in cathode only the pure metal will be deposited. So this is how you can purify copper or any other metal as such. Now the next one is electroplating. Now electroplating also you have an idea in your previous classes itself. So electroplating is a method by which we are going to coat or plate a particular element with a desired other metal. Okay, we are going to plate or coat one metal using another metal. So how can that be done? For example, I have a key here. Okay, so the key that I have to coat with copper. Okay, so I am going to coat the key using copper. So the key will be made of a metal, right? I want to coat that particular key using copper. So this method is called as electroplating. That is, a thin coat of a metal is given to that particular substance, right? So now here also what you have to remember, the substance that requires to be coated, right? Now the key has to get coated, right? So the key is going to be taken as the cathode, and the metal that you want to coat, that is going to be your anode, right? So same way, anode, what is happening? Oxidation will take place and Cu2 plus will be formed, right? Oxidation will take place, Cu gets converted into Cu2 plus, oxidation happens, and what happens here? In the solution, the Cu2 plus ions will be there, right? It's a copper sulfate solution. Cu2 plus ions will there. It accepts electron and forms copper. And what will happen? The copper get deposited on the key. Right, copper will get deposited on the key. Right, so the same process that is happening here, the exact same thing is going to happen here. Instead of purifying, we are going to take up the copper from here, it undergoes reduction here and the copper will get deposited here. So whatever is the substance that you have to coat with, that you are going to take as the anode, and to which substance you have to do the coating, that should be the anode. So this you have to remember. Right, moving on to the next one, that is quantitative aspects of electrolysis. That means just now we discussed, right, in electrolysis what is going to happen? Through the passage of electricity, electrolytic solutions is going to decompose and either a substance will be formed, deposited, right, in the anode or cathode, a substance will be deposited, or else some gases can be evolved. So now how much amount of the substance is being formed, or how much amount of gases is being evolved, we can calculate using these laws that we are going to study. So that is why it is called quantitative aspects, that is how much amount of the substance is getting deposited or evolved is being calculated using this particular law. So these laws are called as Faraday's laws of electrolysis. So there are two laws that we have to study. The first one is Faraday's first law. So here what is important to remember the statement. Right, what is Faraday's first law and the equation also. Right, so the amount of substance deposited or liberated at an electrode is directly proportional to the quantity of electricity passed through the electrolyte. So it means that, yes, I told you in electrolysis, some substance gets deposited or some gases will be evolved, right? So the amount of substance which is getting deposited is directly proportional, or it completely depends upon how much of electricity is passed through the electrolyte, right? In electrolysis, what happens? Electricity is passed and decomposition of the electrolyte will take place. Substances will be formed, right? Now, how much of the substance is formed will directly depend upon how much electricity is being passed. So what does that mean? The amount of substance, that is the mass of the substance, is directly proportional to the charge of electricity, or how much of electricity I am passing through it. So the mass will be directly proportional to I into T. Can I write? We know that charge is equal to I into T, right? Q is equal to I into T. In physics, you have already studied this equation. So mass of the deposited substance, right? How much mass is deposited is going to be directly proportional to the quantity of electricity produced. So instead of Q, I can also write it as I into T. So the final equation I can write W is equal to Z into I into T. Now this Z is a constant which is used to remove this proportionality, and this Z is called as electrochemical equivalence. Z is called as electrochemical equivalence. So this is the equation that you have to remember. W is equal to Z into I into T. W is the mass of the substance which is deposited. It depends upon electrochemical equivalence. I is current and T is the time. I hope it is clear. So this Q I have written as I into T. Right. Now what is electrochemical equivalence? It's the amount of substance deposited by 1 ampere current which was passed for 1 second. So W and Z will be equal when I is 1 and T is 1. Right. So we can define electrochemical equivalence as the mass of substance deposited when current is 1 ampere, time is 1 second. Okay. So this is Faraday's first law. I hope it is clear. That is, how much amount of substance is deposited, it will be directly proportional to the amount of charge or amount of electricity which is passed through it. So the equation is W is equal to Z into I into T. Right. Now, the amount of electricity required for oxidation or reduction depends upon the stoichiometry of the electrode reaction. The charge on one electron is equal to 1.6 into 10 to the power minus 19 coulomb. In last year itself, we have studied what is the charge of electron, right? It is 1.6 into 10 to the power minus 19 coulomb. Therefore, charge on 1 mole of electron will be 6.022 into 10 to the power 23. That is Avogadro's number into the charge of 1 electron. That will be the charge on 1 mole of electron. That is 96487 coulomb per mole. So instead of taking this value for numericals, you can see take the value as 96,500 coulomb, right? And the quantity of electricity will be N into F. Now, what does this mean? That I have already mentioned that the value of Faraday's constant, that is 1 farad, is equal to 96,500 coulomb. Now, from where this 96,500 is coming? That is the charge of one electron into the Avogadro number. That is 1 mole of electrons, how much charge it is carrying. That is 96,500 coulomb. So, that is your 1 farad. Now, what does this mean? The quantity of electricity is equal to N into F. N is the number of moles involved. For example, if you are taking the example of the Daniel cell, that is zinc gets converted into Zn2 plus and 2 electron, and copper accepts these electron and forms copper. Right, Cu2 plus accepts the electron and forms Cu. Now, in this case, how many electrons are involved here? 2 electrons are being involved. So, in this case, the quantity of electricity that is being passed is 2 farad, right? N into F, 2 farad. So, it will be 2 into 96,500. So, it also depends upon the number of electrons which is involved. The quantity of electricity will be N into F. Okay, so it's not just F we are calculating, it will be N into F. Depends upon the number of electrons also. And the value of 1 farad is 96,500 coulomb. Now, moving on to the second law. Okay, again the definition, that's the statement, and the equation is very important. When the same amount of electricity is passed through different electrolytic solutions, then weight of the substances deposited or liberated at the electrode are proportional to their equivalent masses. Okay, now what does that mean? I have 2 different electrolytic solutions. I have one electrolytic solution here. I have another electrolytic solution here. Now, the same amount of electricity, okay, or the same quantity of electricity is passed. Okay, I'm connecting it using a wire. Now, the same amount of electricity is passed through both the electrolytic solutions. In that case, on what does this mass depend? Will the mass deposited be equal? Let's take the example here. I have taken zinc. Okay, zinc sulfate, and here I have taken copper sulfate. 2 different electrolytic solutions. But the current I am going to pass through it is a constant value. It will be the same amount of electricity I am going to pass through both the electrolytic solution. But still, the mass deposited will be not the same. It will depend upon the equivalent masses of the substances we have taken. So, the mass of substance deposited will be directly proportional to the equivalent mass of the first substance, and the mass deposited of the second substance will be directly proportional to its equivalent mass. So, we can also write it as W1 by W2 is equal to E1 by E2. So, this can be also asked in the form of numericals. Either one of this value will be asked to calculate. So, you can rearrange and write. So, W1 and W2 will be the masses which will be deposited in the first and second electrolyte solutions, and E1 in E2 will be their equivalent masses. I hope it is clear. So, these are the 2 laws. The Faraday's first law states that how much mass is going to get deposited is directly proportional to the quantity of electricity that we are passing. The second law states that I have 2 different electrolytic solutions, but I am passing the same electricity. Then, how much mass is going to get deposited in each of these electrolytic solutions will be directly proportional to their equivalent masses. It doesn't depend upon electricity because we are passing the same electricity, right? So, then it will depend upon the equivalent masses. So, this is Faraday's second law, right? So, in the next class, we are going to study about products of electrolysis. So, I hope the concepts that I've covered in this session is clear for you. So, that's all for today. Thank you.